So, good morning. Welcome to Krishna's classroom. We start with another episode of the lectures on Lebesgue integration theory. Now, in this talk, we start getting an idea of how to construct the Lebesgue measure on as large a class of subsets of the real line as possible. Okay. We would be very happy if we could do it for all subsets of the real line, but then you see that the objective is to define a set function on a class of subsets satisfying certain conditions, and the conditions put a constraint and possibly rule out some of the sets from this consideration. That we shall discuss later. But let us begin with this our journey to start with what is called the. Now I think from now on I think we are going to take up a very rigorous path. So we take R, the set of real numbers. Then you have R star equal to R that means you adjoin both plus infinity and minus infinity to it, and this is required because we want to go beyond bounded functions and allow the functions to take infinite values at infinity also. So that's the reason why we consider R star. Okay. Now we will be considering functions defined from R to R star. That is our objective. But from whatever we have discussed so far, we have seen that the Riemann integral, the concept of Riemann integral is restricted, and therefore we have to go beyond that, especially the problem of completeness of certain metric space come into play. Therefore, we have to go beyond that and get more functions captured under the integral, which should be in a way an extension of what we have done, what we call the Riemann integration. That means wherever the Riemann integral works for those functions, the new integral that you define has to coincide with the Riemann integral. So that is one restriction that we would like to keep. Okay. Then we found that the strategy is to get a large class of subsets of R to be brought under the requirement of finding a length. Now, that means we go beyond what are called intervals, because in Riemann integral we found that it is sufficient to talk about lengths of intervals. Okay, that we have seen. So we want to go beyond that, because our strategy was take the range, subdivide into intervals, pull them back using the given function, and what you end up on the domain may not be any more an interval, and where you need the concept of length to be introduced. Okay, right. So what we require is, we are cautious at this moment So we want to define a set function. So the length function that you introduce is certainly a real valued or an extended real valued function defined on the subsets of R. So that's something that you observe. Which we called a measure. Is an extended real value. Defined on a collection of subsets of R with certain properties. What are the properties? So let script M denote the subset of the set of all subsets of R denoted by PR. Okay. On which we wish to define the measure. So what are the properties that M should have? First of all, that comes from what we ask for the functions M. So you see that the measure that you define. So let denote the measure. So M is now a function from the script M to ask. What are the properties that we want M to be? M of zero for every A belonging to then we want the following properties, that the measure of intervals should be equal to length of intervals. For every interval I. Where Li is the length. So measure is essentially an extension of the concept of length from intervals to a larger class of subsets of R. Okay. Now what more you need? You need the M should be translation. X belonging to R. That is M is translation. These are the desirable properties I am writing. And you also should have measure of the union AN 1 to infinity should be equal to sum of the measure of AN So first of all, the measure should be defined for union of AN, and that should be this whenever AN belongs to M and AN intersection AM is empty for N not equal. So if this is a disjoint collection, then we would like the measure of the union to be equal to sum of the measures of the components. Okay, these are the desirable properties that we are looking forward to. Okay, therefore we can now ask for the set to have some structure. Therefore, what are the things that you ask for? We would like possibly the empty set to be a member of M. So, comma, A belonging to M implies A complement belongs to M. So that of course the whole X or the whole of R is now in this class. Then you have union of that is countable union of the sets in this class M should be also. Okay, so these are the conditions that you need. This A belongs to M implies this. So 1, 2, it's some minimum conditions that we are imposing on the collection script M so that we can comfortably define the function. It's all coming out from the requirements, right? What should be the measure that we have listed out? What are the desirable properties for that? Therefore, it is a function defined on a class of subsets of R, and therefore we would like that class of subsets of R to possess certain properties so that We don't have to bother about it. We are comfortable defining this function in whichever way we define it. So we'll be concentrating more on the definition of such a function. Yes. Now it's not an easy task. Now we would like, of course, if A belongs to M, we should write A plus X belongs to. These are the properties. Desirable properties for the collection M. Such a collection is what you call a sigma algebra. Okay. So we should be defined that's called a sigma. A subcollection script M of the set of all subsets of R is said to be a sigma algebra if the following properties are properties are satisfied by so what are the properties that we ask for? Okay, let us look at the properties that we ask for. First of all, empty set should belong to M. Second property is that if A belongs to A complement, third property is that implies union countable union of An belongs to. Now the consequence of this is that it is immediately true that from 2, you have the whole of R M, because R is the R complement or phi complement in R is R. So this belongs to M. The other property that is true is that intersection of AN also belongs to whenever so the collection is closed with respect to countable union and also closed with respect to countable intersection. The empty set should be there, which implies R is in this class, R belongs to M. Then you have this property, that means it is closed under countable union, and from there you can, using the second property, it is easy to show that this is closed under countable intersection. So this collection M is having empty set, the whole set, okay, and then it's closed under countable under complementation. That means if A belongs to M, then A complement belongs to M. Then it is closed under arbitrary union, countable union and countable intersection. Because we don't go beyond that. Okay? So this is what you call countable union. It's countable intersection. Such a collection is what you call a sigma G. That's sufficiently done. Now on that we have to define. Now you see the basis is there to define the the measure, okay, right? Except that, of course, we would like to have A plus X also in A whenever E is in M, whenever A is in. So that is true. I mean, that we shall not include here at this stage, but later, and whatever we do and the way in which we define the measure, see that this is automatically taken care of. So we shall not include this in the definition of sigma algebra. Now what we do is, we have to have all the intervals in this collection, okay. So let us see how we work on this collection. So this is a general sigma algebra that we have defined. Now what we would like is this. Now we see that we have, you recall what happened. Suppose you have disjoint intervals, then what did you choose to call, or what is that you can call the length of this set? That is, you have an interval I1 and an interval I2 such that I1 intersection I2 is empty. Then we would like to write or L of L. I put it in the inverted commas because this is not the length. L of, because I1 intersection I1 union I2 is no more an interval. Therefore, it is not the usual length. Now, this we set as L of so to intervals we would desire to have the desirable property that you have is this, as we have seen here. Now you see you have some nice theorems. Now you see that every open set can be brought under this. Now what we are doing is, we are not considering R as just a set of points, but having a topological structure also, which is the usual, coming out from the usual concept of length that we define on R. So once you introduce that, you have the concept of open sets. So as the that means D of once you have it, then we can talk about the open and closed sets. The open sets and closed sets. Especially open sets. That's what we are looking. And there are sets which are not necessarily open intervals, which are also open. Okay, you have the usual definition of that. So one of the nice theorems that you can prove is this. We call the following theorem. If A contained in R is an open subset of R, then A can be written as countable collection of That is, their excess a countable disjoint. Their excess intervals A and B, which are open comma IN intersection IM is empty whenever N is different from M. Such that the given set A, see, this is an open subset. The given open subset A is essentially equal to so this is a very crucial important result which we shall use in our analysis. Okay, so this theorem is very important. We call the whole. So I will mark this. Which are open. IN intersection IM is empty whenever N is different from M, such that this is true. Now this is a very important theorem which allows our analysis to be pushed across. Okay, so that's something important. Therefore, in this case, what is the advantage of this? Therefore, we can now the length concept extended to all open sets. All open sets. By setting length of A equal to sigma length of IN, and that is equal to, by our definition, so length of A is now equal to so we will have this is equal to N equal to 1 to infinity N of Y. That is as a sum of this, namely whereas In is equal to In, of course, is the open interval A and B. Okay, so it looks naturally this is something that we would like the length concept to be introduced to this. But now that is not enough. It's not enough that we take up only open subsets of R. See, here this could be even infinite. Okay, because if A happens to be the whole of R, then this has to be infinite. So all these are non-negative. So all those properties are that. So we will look into it in detail. But this length concept to union of intervals alone, open sets. We need a larger class of subsets for which a length concept is to be introduced. So what we have is for open sets you have the length. For all open intervals you have the length. Now you know that the crucial result is that every open set can be written as the disjoint union of a countable collection of intervals. Okay, or a countable collection of intervals which are mutually disjoint. Okay, and that allows us to extend the concept of length to all open sets, but that is not enough. Okay, because there is no guarantee that the pullbacks that you get with some functions depends on the function, may not be an open set at all. So we would like a larger collection to be amenable to the concept of length that we would like to use. That's our problem. So still we have not talked about what this script M is. Okay, so we will bring in that or make it clear later, but we take it some sigma algebra of subsets of R which contain all the open sets. Okay, not merely this. We may have to go far beyond just the open sets and everything. Okay, so you have okay. And up to that we are comfortable. and closed sets in R, and of course we would like to have empty set and R find comma. Okay, right? So you have to go far beyond the collection of open sets, and that's something that is required. So how to reach out to that and define what is called a length for such functions. Now you see that we have seen the desirable properties of the length includes the following. It is a non-negative function and it may take even infinite value. So it is an extended real valued function which is non-negative. Secondly, for a disjoint collection of sets in M, their union also should belong to that, and therefore we would like to have the length concept defined for that, and then it should be countably additive and it should be translation invariant. Now these are the properties that we would like to have, because the length is translation invariant, therefore you would like the whatever you construct also becomes a translation invariant function. And it is a natural extension of what is called the length function that we introduced. That's what we want. Okay. Now what about the length, or what we have chosen to class to call M? So M is a map from M into okay, with the following properties, that was every interval belongs to M. So you should have M of I equal to length of I. That is, the script M should have all intervals. That is something. Right? Then you have M is translation invariant. First property. Second property is M of A. That is, M is Third property is that now the difficulty that we face is the following, that m is not any arbitrary extended real valued function on script m, but satisfying these set of properties. Okay. Therefore, suppose you see that one of the observations that we make is that so note that probably the largest sigma algebra subsets. Now we would possibly like script m to be PR. Can you have it? I mean, that's a question. The second condition that you have is this. Now you see, you have to have these properties valid. Okay. Therefore, see, the measure of interval should be length of the interval. So all intervals are in this class, and for which the measure has to be equal to the length of the interval. And then you have translation invariance, then the countable additive property. Is it possible to have such a function defined on the entire PR? Later we shall see that for a set function m to exist with the properties. We have to forego the luxury of that means we have to drop out some sets from PR may have to be thrown out to get that is one of the problems that we face because of these stringent conditions that we use. Okay, so how do we go about doing it then? And you know that there are infinitely many subsets on R. Therefore, it's a big problem now. Find out the or to fix the length function with all these nice properties. Okay, all these desirable properties. That is a length that is crafted from the usual notion of length for an interval or its generalization as its generalization. Now this is rather difficult. So we choose the following procedure. We construct something short of a measure. Okay. So what we do is construct a set function on PR. That means a function from PR to the whole of R, which falls short of we keep the new function m star from to be translation invariant, coinciding with the usual length for intervals. That means m star of to m star of then it should be not countably additive but countably subadditive, and m star of union 1 to infinity an less than or equal to okay. It's a non-negative function, non-negative extended real valued function with this property. For every Here you see that we have replaced the demand of the function being countably additive by the requirement that it is countably subadditive. Okay, this is subadditive. It's called countable subadditive. Okay. So for intervals, m star becomes the length. M star is translation invariant because m star is a non-negative function. Non-negative extended real valued function. Such that for intervals it gives you the length, it is translation invariant, and it is countably subadditive. It's not additive, not necessarily additive, maybe additive also, may not be in some cases, but in general we do not ask for that stringent declaration. It's quite easy to construct many functions with these properties. Okay, but we will try to work this out in a way in which we want everything to be possible. So how do we possibly construct it? Okay, so we call as the outer measure. And denoted by oh, this is the path to get a measure. Okay, now how do we define this? So we'll take a definition. Let is one of the subsets of R. Now for that define m star of A to be equal to infimum of sigma one to infinity length of in. Now the infimum taken over all collection Okay, with the property that A is contained in union equal to 1 to E. So what we do is we take A, wrap it up inside this a collection of intervals, a countable collection of intervals. So the strategy is this. Wrap it up. Collection of intervals. That is, A is contained in okay. Now over all such possible wraps, okay, for each such wrap you compute length of I. Now you see that one thing, okay, you know that LIN is greater than or equal to 0. Therefore, this sum is either finite or infinite. Okay. Therefore, you see that you get a collection of numbers which are bounded below by 0. Okay. Right? Because you see that LIN is certainly greater than or equal to 0. Therefore, the collection of such numbers is bounded below by 0. So what can you say about this collection? The infimum exists. Okay. These sums are bounded below by 0. Right. It is non-negative and bounded below by 0. Non-negative and bounded below by 0. Therefore, the infimum exists and is certainly greater than or equal to. Okay. So that infimum is what you define as the M star. So M star of the over the infimum taken over all such collection of intervals whose union has A as a subset. Okay. Now this is well defined and there is no ambiguity at all, and this infimum exists, and that is what you call star. This M star is what you call the outer measure. And is defined for all subsets of that is for every A belonging to here. This is what is called the outer measure. Okay. So we have defined what a outer measure is. Now we shall explore what all things we get out of it. What are the properties of it? So the question that you take up next is so that is the concept of outer measure. Okay. We shall see that we shall prove that this has all the properties other than what is called countable additivity. In fact, you can prove that it is countably subadditive in general, but not in some cases maybe additive also. Not ruling it out, but it's countably subadditive, and that is that equality being replaced by inequality. This is a more liberal or a more generous condition that you use. Therefore, it is not difficult to get that true for all subsets of PR. That is something that you should observe. But if you insist on countable additivity also along with the other properties, then you see that we may have to forego the luxury of defining it on the entire PR. It will get defined on a smaller class of subsets. And if that includes all the desirable sets like open sets, closed sets, okay, and then any other subsets which come into, which we normally you would come across when you take F inverse of an interval for a given F, then that's good enough. So we'll try to do that. We'll try to work out. So we would like to make this as large class as possible, but sometime or other, towards the end of it, show that it is not possible to have it defined on the entire PR. So that means you will have to be satisfied with you want to retain all these properties that are desirable for the measure, then you will have to necessarily restrict the facility to be available only on a subcollection. Nevertheless, that subcollection will have very nice properties, and that would eventually give you what is called measure. Okay? So you have to craft from this what is called measurable sets. Okay, right? All the subsets have outer measure, but the measure that you craft from it would be defined only for a proper subcollection. That means you are able to show that there are some sets, some subsets on which the measure that you define is not going to satisfy all the requirements of the measure function. Okay, with this I stop today. So, thank you very much. Now we would start working out properties of M star. That is our next task. Thank you very much.